Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on December 9th, 2025, about 3 days ago. This paper introduces a vision language model that keeps latency and memory essentially constant, while giving over 3.6 times faster inference, yet still matches leading transformer-based models, using less than 2% of their training data. The paper is titled InfiniteVL, Synergizing Linear and Sparse Attention for Highly Efficient, Unlimited Input Vision Language Models. And as we will see later, the implications for long context multimodal reasoning and real-time video understanding are quite significant. Also, the authors shared a full GitHub repo. So if you want to play with InfiniteVL yourself, you'll find the core Python implementation, environment setup via requirements, example scripts for streaming video inference, assets for demos, and links plus instructions for loading the released 4B model checkpoints and variants. Figure 1 shows that InfiniteVL delivers the same or better accuracy while being dramatically more efficient than the transformer baseline. The left panel compares bars for training throughput, streaming frames per second, cache size, and per token latency, where the yellow InfiniteVL bars are consistently higher or lower in the right direction. The right scatter plot places models by average benchmark score versus frames per second. InfiniteVL sits alone at the top right, which means strong performance while sustaining true real-time 24 frames per second streaming. Figure 2 explains how InfiniteVL actually wires that efficiency together. The full diagram shows visual tokens from the naive resolution vision transformer, and text tokens flowing into stacked hybrid blocks, so images, video, and text, all share one processing pipeline. Inside each hybrid block, the left blue region is a sliding window attention layer, which focuses on nearby tokens for fine local detail. The middle blue regions host 3 gated DeltaNet layers, which maintain a compact running memory so the model keeps long-term context without growing its cache. The green column tracks this memory cache as it updates, which is what lets inference speed and memory stay essentially constant even as input length grows. Figure 3 explains how the model is trained in 3 stages, so it learns powerful skills without huge data or compute. The left panel shows stage 1, where a full attention teacher model guides a student that swaps in gated DeltaNet while keeping most other parameters. The middle panel illustrates stage 2, large-scale supervised fine-tuning on diverse multimodal instructions to teach following directions and reasoning. The right panel depicts stage 3, where long sequence data with high-resolution images, documents, and videos extends the model's context length while preserving both local detail and long-term memory. Table 2 shows that InfiniteVL keeps constant time complexity, yet matches or beats transformer models on text-heavy reasoning benchmarks. The top block lists transformer-based vision language models with quadratic complexity, while the bottom block lists linear and hybrid models. InfiniteVL reaches the best average score in the whole table, which means it handles charts, OCR-style reading, and math reasoning very competitively, despite its lighter architecture. So Table 1 focuses on broad, multimodal understanding and real-world question answering, and it shows that InfiniteVL reaches top-tier accuracy while keeping constant time and memory per token. The upper block lists transformer-based models, whose complexity grows linearly with sequence length. The lower block lists linear and hybrid models, where Cobra and InfiniteVL have constant complexity. InfiniteVL not only has the highest average score in that lower block, it actually surpasses most transformer baselines, despite using the more efficient architecture. Figure 4 shows that InfiniteVL keeps both performance and speed stable, even as videos get very long. The left 2 panels track accuracy versus number of frames, and InfiniteVL stays flat or even improves, while the pure sliding window model collapses once it passes its window. The third panel compares per token latency, which remains almost flat for InfiniteVL, but grows steeply and hits out of memory for the transformer. The rightmost panel shows streaming frames per second, where InfiniteVL holds real-time 24 frames per second, while the baseline quickly slows down to a crawl. Wrapping up, the big takeaway is that InfiniteVL shows you can get transformer-level multimodal accuracy with constant time and memory by smartly mixing sliding window attention with a gated linear memory. That unlocks practical long context and real-time video understanding on modest hardware. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.